Hello, yeah, thank you everyone for coming. My name is Andrei. I'm a PhD student at the Institute of Science Technology Austria, and today I'm gonna talk about the latest paper that we did on low precision pre-training. It's called Quartet, and the idea for this paper that we had is that we both wanted to develop a more accurate framework of describing low precision training trade-offs and to be the first to design a native FP4 training framework, a native FP4 training method, which would allow us to achieve optimal precision to speed the trade-off for large language model pre-training. And let's start with understanding why low precision training is useful at all. And I briefly mentioned it already because we do low precision to achieve speed ups from the various data types that are available on modern accelerators. More specifically, modern accelerators usually treat BF16, FP16, and similar formats with 16-bit per parameter as the standard precision. And when we decrease the precision from those formats down to more basic data types, such as integer 8, FP4 or FP6 tensors, we can achieve speedups that are proportional to how much we decrease the data type. For example, on the B100 GPU, the latest Blackwell generation GPUs from NVIDIA, those data types, the main data types that they push are FP4, FP8, and even implicitly they support binary operations, meaning that you can achieve up to 16x speed up on the operations that you want to perform. And more specifically, I mean matrix multiplication operations, because modern deep learning models and large language models specifically mostly consist of matrix multiplication operations. Meaning that if we can, meaning that going to lower precision data types when using our models, we can perform those matrix multiplication operations in lower precision and achieve theoretically proportional speed up to how much we compress the data type in which we perform inference or training of large language models. And one additional thing that I want to say about data types is that this FP4 data type that's present on the Blackwell generation in the GPUs isn't a simple FP4 data types, but rather a microscaling data type, meaning that it explicitly supports a grouping of values and group-wise scales for values. More specifically, MXFP4 supported on this Blackwell generation of GPUs supports FP4 vectors that are scaled by integer exponents for one scale for every group of 32 values, meaning that this data type has a low structure and hardware support for this local low-level structure in groups of 32 elements. And now that we know what the profit of low precision pre-training is, we can try and understand how to do it and what we lose when we do it. And to do that, we can take a look at the previous literature that's available on this topic. Here I'll be taking a look at a few methods and provide a few quotes from the papers that describe how exactly they measure their speedups and how they describe the accuracy degradation that's inherent to using lower precision data types instead of baseline full precision training. And the first method that I want to take a look at is LUQ, which is lookup quantization. And they mostly tested their method on vision models, and they described the usefulness of their method by demonstrating that it only drops about 1% of accuracy on ResNet 50, which is 2x improvement over previous SOTA. And regarding speedups, they did for training before it was actually supported in hardware, so they couldn't provide any actual end-to-end speedups to justify why it's actually useful to drop 1% of precision. So the gains there also theoretically make sense because lower precision should in theory allow you for faster inference. Back then they couldn't actually show this inference speedup. Another method that is much more modern that was first shown early this year is Halo, where they use low precision matrix multiplications to train large language models. And in terms of accuracy, what they demonstrated can be pretty much summed up by the quote from the paper when they say that they simply maintain close to baseline accuracy without going into much details what they mean by close and how much closer they're than other methods. They do have baseline comparisons, but they don't have a very fine-grained justification for why their speedups justify the drops in performance, because they mostly focused on the speedups themselves. And this is, and in their paper, they provided actual kernels for in-date and the FP4 end-to-end training and demonstrated quite remarkable speedups of almost 40% for end-to-end lemma 3 fine-tuning. Another paper we might take a look at is Jetfire, where they again simply state that they incur exactly no degradation compared with the floating point baseline. And again, mostly focus on speedups that they can provide, where they focus on matrix multiplication speedups and overall forward-backward training speedups. Another paper which does integer 4 end-to-end pre-training again simply states that it achieves competitive accuracy without going into much detail of how much it actually drops, or at least not analyzing the trade-off between the speedup and the accuracy drop, while again focusing on speedups that they're able to achieve, where for the matrix multiplication itself, they show 2.2x speedup over FP16, and for end-to-end training, they show 35% speedup. And what we can infer from looking at all those papers, if we take a look at how they describe accuracy, we can see that all they're trying to do is recover the FP16 or the baseline accuracy as closely as they can. And they usually measure this accuracy for a very narrow setup, meaning that they train a very specific model with a very specific size and a very specific data set and measure accuracy drop as, for example, percent inaccuracy or the validation loss for language modeling. And the problem with this approach is that it's very narrow in a sense that these drops depend on the exact task you're measuring on the model size that you're training on, how long you're actually training it. And they usually don't look at forward and backward path quantization separately, measuring only the drops for the entire method. Or at least they're not trying to connect these drops and separately describe their performance and then build a model on top of it. In terms of speedup, the problem with speedups is that they usually only show their speedup and show that they're either faster than all of the baselines or that they're faster than some abstract baselines such as BF16 precision, than BF16 full precision training. And they also usually show speedups for a very narrow set of model sizes. And this is important because the speedups are dictated by the kernels that you're implementing, and they depend a lot on which exact models you're running and which model sizes and batch sizes and sequence length specifically for large language models you're running. They also don't take into account often that the forward pass and backward pass speedup is vastly different, as for example seen by LSS, where the forward pass precision or linear matrix linear layer operator speedup is 2.2, but the full forward backward end-to-end speedup is only 35%. So when this model compare against different baselines, what they usually want to do is they want to either show that they're faster and have identical or better quality than some other method. For example, we can see it when they say that when they say that they don't lose any accuracy, and they say that they have any speed up over BF16, it's very easy to see why this method is more optimal than BF16, because you obtain the same quality model for cheaper. Another way how one can easily show optimality is if it has identical speed but yields better quality models. But the problem is that to perform those comparisons, you need to compare models of same size and same data, and ideally of same quantization method to be able to show exact speedups and take a look at them. And this heavily limits how you can build comparison between methods, because it's very often that different quantization training methods show both different accuracies of the results in models and different speed ups that they can show over some baseline, meaning that there exists a trade-off between speed up and accuracy that cannot be described in terms that these previous works usually use, where they want to show a clear win over the baselines. So what we might want to do to compare different methods is we might want to design a framework which would allow us to compare methods to more accurately describe this accuracy to speed up trade-off, and ideally not only for some fixed model sizes and fixed training durations, but rather in some aggregate way that would take into account possibly different speed ups for forward and backward pass of the method that you're using, possibly various model sizes and training durations for the models that you're training. And ideally, this framework would even allow us to extrapolate our findings to know which models would be optimal even before we actually train those models, to make predictions about the optimality of certain precisions. Well, this is one of the goals of our paper, and to do this, we provide 4 ingredients for guidelines on how to actually design this comparison and what we can do to address all of the issues rising from this comparison. So, taking a look at the first ingredient, we want to build a predictive model of our model's performance to be able to extrapolate performance. And to build this predictive model of model's quality, we use scaling laws. Scaling laws are parametric functions of model training hyperparameters that are fitted on the actual training runs results to be able to extrapolate the loss function predictions and predict the performance of our models even before we actually train them. So in general, scaling laws were proposed multiple times over the past years. They were proposed initially for finding some compute optimal model configurations, for example, where we can trade off parameter count for data for the number of chain tokens to find the compute optimal model loss. Or they were proposed to extrapolate performance and find optimal hyperparameters for training larger models before you actually train them. And here we use the scaling laws to model the effect of quantization and predict the effect of quantization on model training without actually having to train those quantized models. We use the following form of the scaling law, where we have this law as a function of the number of parameters in the model, number of tokens it's been trained on, and the forward and backward pass precisions of our quantization-aware training scheme. And in general, in some form, this scaling law has already been proposed. because the idea to model the effect of forward pass quantization as a multiplicative factor on the number of parameters has been proposed numerous times. But modeling the effect of backward pass quantization on the number of tokens that we're training is novel, and to the best of our knowledge, we're the first to propose this. And basically what this formula says is that forward pass quantization mainly affects how efficient the parameters of your model are, with the heavier quantization degrading the performance of the model more, and leading to larger models that perform worse than their unquantized counterparts. And the backward pass quantization mostly affects the amount of data that the model is trained on, meaning that you would have to train the same model for longer to achieve the same loss. And this form is consistent with optimization theory that says that if you have some noisy estimators of your gradient in your gradient method, then you would have to train for longer to achieve the same loss, or that generally that your convergence rate would be slower and not necessarily the point that you converge to worse. And when to use this scaling law, we first have to fit it, and fitting the parameters, the parameters A, B, alpha, beta, gamma, E, and the efficiency factors for a number of llama family models from 30 million parameters to 200 million parameters saturated with different amount of data in a range from 25 to 800 tokens per parameter. We capture a very wide range of both parameter counts and token counts for this scaling law, and we demonstrate that it can very accurately fit the losses and very accurately predict models' performance when training models with quantization-aware training. So one question that one might ask is that if we want to use this scaling law for performance extrapolation, we need to be sure that it actually extrapolates well. And this is sort of a question of how to verify that your scaling law extrapolates without actually running larger runs and thus interpolating instead of extrapolating. And for this specific scaling law, we have a few arguments why we believe that it's representative of model performance across larger model sizes that we didn't explicitly test, because the same form was proposed to model large language models performance, always without quantization, was tested up to 7 billion parameters models by Busbridge and co-authors, who also proposed this general form with the alpha, beta, and gamma coefficients. In our previous paper, we actually tested a very similar scaling law with a slightly different form. That parameter gamma was fixed to 1, and we didn't quantize the backward pass, and we tested it up to 1.6 billion parameter models and shows that it's stable and it fits data well. Additionally, Albert Tseng and co-authors who published an interesting paper on backward pass quantization, which we actually used in our paper as the backward pass quantization method, tested that their method provides stable performance up to 7 billion parameter model training, meaning that the law probably doesn't break in that regime either and shows consistent performance. And even though ourselves we only trained models up to 200 million parameters, from everything mentioned above, we conclude that this scaling law is probably stable for higher parameter counts as well, and we can use it to extrapolate model performance and make predictions about the quantization-aware training for even larger model sizes that would be very expensive to test explicitly. So regarding this ingredient of quantization-aware training design, we show that we can accurately describe the loss of quantization-aware training in the form of a scaling law. And as such, we can describe the effect of quantization itself in a form of a scaling law. And one can see that instead of comparing losses for the same parameter count and data count model runs and showing that one method is better than another because it leads to lower loss, we can simply compare the efficiency factors of quantization methods to say which ones would be better or worse for practically any training hyperparameters that you can come up with within the scope of the scaling law. More specifically, we say that if a method has better efficiency factor on parameter count, it's and better efficiency factor on data count, then it will lead to better loss across all model sizes and data saturations, and as such, we can say that we can conclude that it's a better method on its own. The next ingredient that I'm going to talk about is that we saw that compare different methods with each other, we need to take into account both the speedups that they provide and the accuracy degradation that they incur. And to do this, we need to accurately model both the speedups and the accuracy degradation. And looking at speedups, we can see that the forward pass quantization and backward pass quantization actually affect speedups in a very different fashions. Where if you were to assume that the speedup going from, for example, FP8 to FP4 is 2x, then quantizing just the forward pass would lead to 2x inference speedup. However, it would not. However, performing backward pass in FP8, the training speedup would only be around 20%, as the training speedup is mostly concentrated inside backward pass, which we don't quantize. In contrast, if you only quantize the backward pass, you don't get any inference speedups at all. However, you get much higher backward pass speedups, about 50%, which allows you to train for longer at the same compute budget. And if you quantize both forward and backward speedups, you get the best of both worlds and achieve both faster inference and much faster training. And in general, we can describe this effect of quantization speedups as follows. So forward pass in forward pass quantization affects affects inference speedups by a lot. It only affects training speedups by a little, and it degrades parameter efficiency from the scaling law form that we proposed before. Backward pass quantization, however, doesn't speed up inference at all, affects the training inference by a lot, and degrades the data efficiency of our training method, as again shown in the previous section. And from this, we can try to build a comparison framework between different methods with different speedups as follows. So if we were to compare models at the same inference budget, then how can we do it? And one can see that if our inference speedup going from one method from another method is 2x, for example, from ideal speedup going from FP8 to FP4, then to fit into the same inference budget, your model can have 2 times as many parameters, because thus it would have exactly the same inference speed under ideal speedups. So to account for inference speedups, we can plug an inference cost normalized parameter count into the scaling law form that we proposed below, meaning that we can take, for example, some reference BF16 parameter count and multiply it by the speed up of our method over BF16 to get the parameter count that would lead to the same inference cost. Similarly, we can do the same for the backward, but it's a little more complicated because it's not just multiplying by the training speed up, the data count, but you actually have to divide by forward speed up, because when you take a model, you lower its precision. Now your model actually has more parameters, so the compute that is multiplication of your token count and your forward pass cost actually increases. And because of this, to normalize the compute between different speedups, we actually need to multiply token count by training speedup and divide it by forward pass speedup to arrive at a normalized compute cost comparison. And finally, we need to plug in the precisions to actually model the performance degradation, which model through these efficiency factors that were present in the scaling law that we proposed. So in the end, what we can see is that we can predict the loss of our method at some inference budget and the training budget as follows, where we model both the effect of quantization in forms of those efficiency factors that degrade performance, and the fact that when compressing, we're actually able to either train larger models when accounting for inference speedup, or train models for longer when accounting for training speedups. And based on this, we can actually, for any model size of unquantized model, or equivalently any training budget and any token to parameter account for an unquantized model, which is a representation for for training budget, we can say which precision would be optimal by plugging in the speedups that are also dependent on which model sizes we use. So to reformulate it for any inference compute budget, which is y-axis on these plots, and any training compute budget, which is the x-axis on these plots, we can predict which procedure would be optimal, and we could plot this optimality in a form of regions where we say that one or another precision is optimal for a certain region of those budgets. And we do it for the simple speedups model that assumes a proportional speedups for lower precisions, with those regions shown in orange. And we actually do it for the real kernels that we provide, where the speedups are also affected by the matrix shapes and model sizes themselves, meaning that those regions will not be as smooth as before. However, they will show the real optimality when accounting for real world inference costs on real hardware with the real kernels that we provide. And the plot on the left here shows which precision is optimal for a certain forward path, which forward pass precision is optimal when backward pass is performed in FP8. And we can see that the optimality depends a lot on the model size and on the data saturation, with models more saturated with data profiting more from forward pass quantization. And from the kernel standpoint, we can also see that larger models profit more from forward pass consideration as well, because it's easier to achieve meaningful speedups for those. And interestingly, what we see here is that most models that have been trained in the past few years actually fall into this region of FP4 being optimal, meaning that if those models were trained and FP4 under the same inference and training compute budgets, they would probably yield better loss. On the right, we see the same plot, but when backward passes FP4 as well, and we can see that the green region is even larger there because the relative speed up of quantizing forward when backward has already been quantized is even larger, meaning that this region is enlarged. And now all of the models that have been trained in the all of the production models that have been published recently actually fall into this region, meaning that this region includes the model sizes and data saturation ratios that are actually useful in practice. So what we have seen is that based on scaling laws and speed ups and careful analysis of inference and training costs, we can actually arrive at the model that predicts which precision is optimal for every model size and every training budget. And we actually see that FP4 training can be optimal. The third ingredient is
Sorry.
more oh, yes, sorry, I don't see the chat. So if
No,
there
no.
are any questions.
Yeah, it was me. I just raised my hand. In the previous question, just to quickly clarify, so what are the sizes of these models of Llama 3 22.5 that's investigated?
So the size is actually on the x-axis in a sense that this
Okay,
is,
okay.
yes, this is sort of a BF16 normalized model size, meaning that,
Okay,
yeah, BF16, that for those models, it's exactly that.
right. Okay,
And
makes sense.
it takes into account that when you go to lower precision, the actual size would actually be higher,
So
but
ineffective.
the inference cost will be the same. Yeah.
Okay, okay,
So
makes
this is like Lemma 370B. Then it's I guess Qwen 2.570B as well, around that
okay.
72B. And then Gemmas are 32, 14, 7, 3, and 1 billion. Maybe I don't remember exactly.
Hmm. Yeah, I was curious. Basically, that typically we expect FP8 to perform better on these larger models. So I was just curious of this range.
So the exact regions that you see here are somewhat depend on your scale and law shape, because one can actually show that from this scale and law shape, these regions, this line will be tilted either left or right, depending on which coefficients is larger, alpha and beta. And here we have beta larger than alpha, which leads it to be tilted right, meaning that our model predicts that for larger models, quantization-aware training will be less useful. But again, you need to make sure that the scaling law that you're using actually extrapolates to the regions that you're going to apply to. And the form that we are using, we are pretty confident that it scales up to 10 billion because it has been verified in those ranges. But everything above, it's more like an extrapolation that we're not 100% sure about, because the actual experiments in that range would be prohibitively expensive.
Yeah, makes sense. Yeah, thanks. Just wanted to
But
clarify.
since on that, I would also add that for all large language models, pre-training runs that those big companies conduct, they actually conduct extremely extensive ablations to test this. So if you really wanted to pre-train an FP470B model, it would make sense for you to actually train at least a 7 or a 20B model to verify that it holds and only extrapolate a little as opposed to extrapolating by 10x.
Gotcha, makes sense. Yeah, I'm
So
generally curious about like the speed up numbers also that came from that. So that answers my question. Thanks.
oh, yeah.
So what was the time that was required to like train uh 1 billion or a 7 billion parameter model? I think so you worked on that.
So the models that we trained for this work specifically only go to 200 million parameters, and I think the largest data saturation 100 million model here took like 4 days on an H100 node. But for a previous paper, we trained a 1.6 billion parameters model, and I think it took almost 20 days on an H100 node, on a full node. And some of the other papers, like the Apple papers that proposed a similar scalar law form, the Busbridge and co-authors paper, where they scale to 7 billion, they spend a lot of compute on it. I think it was hundreds of thousands of GPU hours to train some of those models.
Mm-hmm. Oh, okay. So I thought you trained from scratch on a 5090 that you have proposed in a paper.
Sorry, what's the question? Yes, we do train from scratch. It's I mentioned those papers more like to show that this scaling law has been verified on a larger scales than we actually do experiments on.
Okay, got you. Thank you.
Okay, so if there are no more questions, I can proceed to the third ingredient of the quantization-aware training design that we propose is that since the forward pass and backward pass have both very different effects on the training, one affecting the parameter count and the other one affecting data efficiency, and different speedups, because forward pass quantization mostly affects inference and backward pass quantization mostly affects training, then it makes a lot of sense to analyze them separately, even from the method perspective as well. And what we show is that those efficiencies vary a lot between methods, and more interestingly, different methods are optimal for either forward pass or backward pass. So in this table, we can see a number of methods. The EPS-max stochastic rounding method that was first proposed for MX FP4 by Albert Tseng and co-authors in a paper that was also presented in the 7R series around a few months ago. The round to nearest variation of the same method, and the quest method from a previous paper of our own that uses a slightly different scaling technique than EPS-max. And we can see that fitting the scaling laws for those methods, we see that the efficiency multiplier for forward pass for parameter count is the highest for quest, a method which was initially designed for forward pass. However, it performs terribly for backward pass quantization for reasons that I'll discuss a little later. And the stochastic rounding with EPS-max performs the best for backward pass. And as such, from this we conclude that different quantization schemes shall be picked for forward and backward pass. And before we define what our final method end-to-end is, let me maybe quickly discuss. I guess we could skip those slides. So this is just a description of the methods that we use for forward and backward pass. For forward, we use Quest, as I said, that uses fast Hadamard transform for weight normalization, weight and activation normalization, and then it uses certain MSE optimal fitting of the quantization grid to perform forward pass quantization optimally. So backward pass uses special scaling factor of 3/4 to make backward pass quantization unbiased. And so this method was proposed, as I mentioned, by Albert Tseng and co-authors. And focusing on it, in their paper, they've shown that this unbiasedness, this stochastic rounding, although it leads to higher noisiness of the gradient, it has a very interesting property that it actually leads to an unbiased gradient estimation. And in their paper, they've shown that it improves convergence, but we went a little further and we tried to describe why it improves convergence and when exactly it's worse or better. And we do it via a trade-off where we mostly compare two methods: the stochastic rounding EPS-max that leads to unbiased but slightly more noisy gradient estimation, and the round to nearest EPS-max, which leads to less noisy but slightly biased gradient estimation. And without going into too much detail on this, we show that stochastic rounding backwards pass rounding scheme leads to better convergence at high data saturations, meaning that the longer you train, the better it becomes relatively. Whereas the round to nearest quantization that is slightly less noisy but biased leads to better initial convergence, but it falls behind stochastic rounding as you increase the training duration. And from this, we conclude that since as we've shown already, lower precision makes more sense for more data saturated models, they fall into this region, and they actually show better speedups and better overall improvements when normalizing by compute. It makes a lot of sense to use the backward pass quantization method that's better for higher data saturations, and because of this we pick unbiased gradient estimation of Albert Senk and co-authors to perform backward pass. So to sum up, our method can be described as follows. So on the forward pass we do quest quantization, and on the backward pass we do the Albert Sank's stochastic rounding scheme to obtain an unbiased gradient estimation. And as like this, we obtain an end-to-end training method that performs both the forward pass and the backward pass in FP4. And as we can see from the efficiencies in this table, it has a parameter efficiency of around 65%, meaning that your model performs the same as 30%, 35% smaller model that was not quantized. And the data efficiency of 85%, meaning that your model performs the same as the model which was trained without backward pass quantization, but trained for 15% shorter. So any questions about how we picked forward pass and backward pass schemes and how we interpret these multipliers?
I had a query for the critical inflection point for the data to parameter ratio. So you have taken it as 400. Like you guys say that this is where this stochastic rounding starts to significantly outperform the deterministic methods. So why is that, and like why is this number so important here?
Why is this number so what?
So important, like the 400, yeah.
So generally we can see this number on this plot because the green lines here are the stochastic rounding, and the red lines here are the round to nearest, and we can see that they intersect at the D2N to around 400, meaning that if you train for smaller than that, you need to use round to nearest to obtain better quality models. And if you train longer than that, you better use stochastic rounding to obtain your models. That would lead to better loss. So this is just sort of a point at which stochastic rounding becomes better than round to nearest.
Yeah, this is for the long training, right?
This is for what?
For the longer training.
Yeah, so for longer training, stochastic rounding becomes better. And since longer training is where quantization-aware training is generally better, as we've seen from optimality regions, we pick stochastic rounding as our main method.
Yeah, true. Thanks.
Okay, so from this algorithm, you can see that it's a lot more than just quantization and matrix multiplication. And from this, we arrive at the fourth ingredient of our method, and this is the CUDA kernels. And the reason why CUDA kernels are important is because CUDA kernels directly affect which method is important, which method is optimal at certain budgets, and thus shapes those regions where certain methods are optimal. And as such, it makes a lot of sense to invest a lot of effort into optimizing your CUDA kernels because it can shift which method or which precision would be optimal for a certain inference and training compute. So to optimize the CUDA kernels for our specific method, we can remember that actually both forward pass and backward pass utilizes Hadamard transforms to normalize the distributions of weights and activations and gradients, and to allow for lower quantization error and for higher parameter and data efficiency. And if we take a look at this operation, we can see that the Hadamard transform here is actually a memory-bound operation on GPUs where the Hadamard transform size is smaller than 256, as also shown by Albertsenko and co-authors in their paper on backward pass quantization. And we can also see that the quantization operation itself, which for MX FP4 specifically is done inside of small groups of 32 values, is also a memory-bound operation because it's always just a load of a matrix, then a projection onto some grid, then a store into back into memory. And since those are two back-to-back memory-bound operations, which are both done locally inside some groups, we can fuse them to effectively cut the cost in half to only have to load once, then perform both the Hadamard transform and the quantization, and then write output once. And this is one of the optimizations that we do for our method, which cuts the cost of non-matrix multiplication a lot. And we make it even more optimal by performing the Hadamard transform as dense matrix multiplication implemented in Kutla's somewhat low-level matrix multiplication template library by NVIDIA, where we can actually specify quantization as an epilogue of a Hadamard transform operation, making it very efficiently pipelined with the data loading, saving, and the computations themselves. Thus, we create this complicated. Thus, we implement this similarly complicated Hadamard transform plus quantize operation very efficiently using some low-level code programming. Additionally, we can see that. Yes,
this is the fuse. This is fused via cutlass, right? Yeah. You have indicated that. Yeah.
Yeah. So the idea is that in Cutlass you can define the custom post-processing script, and we implement quantization as post-processing in Cutlass, and this is why it's very effective. Yes. So if you take a look at the method, which I won't show here again because it's very large, you can see that there on the backward path specifically, there's a lot more operations that are memory bound. For example, there's operation that transposes a matrix, applies a Hadamard transform, and quantizes. And again, we can also just merge all of those operations into one operation by manipulating Cutlass templates, memory loading patterns, and those quantization epilogues to implement them very efficiently and allow for higher speedups. And also there is the metrics, the mask application from Quest and the inverse Hadamard transforms from there, which can also be merged into one memory bound operation, and again optimized to make very efficient on GPU. That's how we optimize our CUDA kernels to actually make FP4 optimal. Other than that, there is the matrix multiplication itself, which is a compute bound operation. That's why we treat it somewhat separately from the quantization operations. And for that, we use custom Cutlass based template tuned matrix multiplication kernels and FP4, which we really hope to make public very soon. And we show that they show speedups that are actually very close to the ideal that are possible under certain tensor core counts and memory bandwidths of modern GPUs. So in general, all those optimizations for the quantization itself, for the matrix multiplication, and for those backward pass operation merging allow us to obtain speedups, which are, again, depend a lot on model size, but for 52B models, for example, allow for around 2.2x forward pass speedup over FP8, around 1.8 around 1.5 backward pass speedup over FP8, and around 1.8 training speedup over FP8 when measured on layers, including those quantization operations and matrix multiplication. One can see here that backward pass speedups are actually noticeably worse than forward pass, and that is mostly because we haven't tuned those kernels as much. We mostly focused on forward pass for now, because forward pass actually has more effect on optimality, because it affects the model size, which is more of a bottleneck when comparing different precisions. And we are hoping to make the kernels for both forward pass, backward pass public very soon. The problem with that is that basically every week we want to publish it next week, and that has been going for around 6 weeks already, but we're really hoping to publish them soon. So any questions about what we did for kernels? So if not, then I can give a quick baseline comparison that we performed in our paper. So to the best of our knowledge, we are the first to design an end-to-end FP4 pre-training method. And as such, the methods that we compared with were mostly either not designed with FP4 in mind, mostly designed for FP6 and FP8 like Halo or Jetfire, or designed for int4 like LUQ or LSS. And as such, they might underperform for lower precision of FP4. And when comparing, we can see that Quartet has noticeably higher both parameter efficiency, data efficiency, and the final losses when compared to all those baselines, with only LSS int4 ever being close to Quartet. However, we also see that the LSS int4 is also an unstable training method, meaning that the training runs diverged basically for every single training run except one when it was close, which means that it has good performance, but it's unstable and as such probably not as applicable in practice. So to sum up, what we do in this paper is we design a novel method to compare different quantization-aware training schemes that is based on the scaling laws that treat forward and backward pass quantization differently, and then uses notions of training budget, compute budget, and the real speedups to determine which precisions are better or worse under certain training circumstances. And we show that many of the models that are being trained nowadays actually fall into the region of FP4 optimality, meaning that in practice it makes sense to actually do train them in FP4. And thank you for coming here, and I'll be happy to answer any questions.